Okay, Assalamualaikum and good afternoon. So we discussed for tutorial 4. So consider steady laminar and incompressible fluid flow between two fixed vertical parallel plates. If the fluid is moving downward between the two plates, use the Navier-Stokes equation to determine an expression for the velocity profile. Please take vertical axis is an x-axis to is our calculation. So in this situation, we have fixed wall like this one. So mean the wall is not moving. And then between these two fixed wall, we have a liquid here. And because gravity is acts on a vertical axis, so means that this liquid will flow downward like this one. So because the Navier-Stokes equation for x, y, and z, the Navier-Stokes equation for Cartesian coordinate is actually the same. So we just replace the element of x, y, or z. So mean it is okay for us to assume that this vertical axis is x, because normally people are easier to remember the Navier-Stokes equation for x-axis. And then this is the equation for Navier-Stokes. So you know that this term is actually come from the du over dt, the capital D, and this come from the idea of nabla square. So please be careful, or please remember what is the meaning of d over dt and nabla square. And then we need to simplify all these terms according to condition that we have. So because we are only focusing one dimensional here, so we assume that the velocity only move downwards. So means we assume that velocity of v is equal to 0 and velocity w is also equal to 0. So because we have a steady state condition here, so we take du dt is equal to 0. So we take incompressible flow. So we assume that the density rho is constant. So please make sure that you really understand when a condition given as incompressible flow, it is mean that the density is constant, not the density is equal to 0. So and then because we assume that the flow is fully developed, so we take du dx is equal to 0. So this is the common assumption that can be used easily in so many situations. So if we substitute all these conditions into the Navier-Stokes that we have here, we could simplify it at this one. So in this situation, it is totally different with situation in tutorial 03 and also 02, because the fluid is moving downward vertically right now, so means that the element of gravity must be exist. You cannot simply neglect the effect of gravity, because actually the liquid there is moving downward because the existence of gravity. And then from the question, there are no statement telling that the pressure gradient is constant. So means that we need to take care the terms of dp dx, means the changes of pressure along the x-axis. So we have these terms. So and then to simplify our calculation, we just bring the negative side into the left hand side. So we could rearrange the equation become like this one. So and then we bring the mu to the right hand side, so we have this term. So and then because we have the differential terms here, we need to change into a common equation. So what we need to do, we integrate the terms. So we know that d square u dy square here, it is actually showing that the differential term is twice. Okay, so we could rewrite as this one. So and then I think you already know about this process. So we integrate this one. So we integrate both sides like this one. Okay, so previously we take the value of dy here, we put to the right hand side here. So and then it become like this one, and then we integrate both sides like this one, and then finally we could get the term like this with a constant of C1. So and then we need to integrate, because this situation we still have the differential terms. We still have du over dy. So we bring the dy to the right hand side. So and then the term is become like this one. Okay, please be careful because you need to bracket this all the terms with dy. So and then we integrate both sides like this one. So and then we could get the value of u as showing in this term. So please be careful. We have two unknown constant parameter, which is C1 and C2 here, that need to be determined. So mean that you cannot leave this equation with C1 and C2. You need to calculate what is the value of C1 and what is the value of C2. If not, you cannot get a full mark for this question. So how to calculate the value of C1 and C2 here? So we discussed it in a previous tutorial. So we need to use the boundary condition to get the value of C1 and C2. So C is actually refers to the constant. Okay, so how to determine the boundary condition? So as stated as it names, so boundary condition mean the condition at the boundary. So boundary means the boundary between the liquid area and the fixed wall here. So we have two places that refer to the boundary, the sempadan. Okay, so boundary between the liquid and the plate. So we assume that the boundary condition number 1 is here and boundary condition number 2 is here. So we assume that this is the y-axis and this is the x-axis. So let's say we take the x here is the positive. It is okay for you to take the positive is upward. I do this because normally, because gravity is x vertically, and we assume that the positive side is actually downward when we calculate the value of gravity. So we have point number 1 here. So we could write the boundary condition like this one. So means that y is equal to 0 because this is the axis of y. So y is equal to 0 and the velocity is also equal to 0. So and then at point number 2 here, so we could write y is equal to h because we assume that the distance here is actually h. So means that in y-axis here, so the coordinate for y is changes from y equal to 0 at this point to y equal to h at this point. So means that we write y equal to h, and the velocity is v is equal to 0. So it is okay to write this one. Please do not worry whether you get same term like this one, so, because it is the correct method to determine the boundary condition. So and then we substitute the boundary condition into equation 1. Okay, so this is the equation 1. Okay, you may refer to this slide later. So please, you substitute the boundary condition into equation number 1. So you could calculate that the C2 is equal to 0. So because the C2 is equal to 0, so means that for the next calculation, we could omit the value of C2. So mean you may write the general equation, means the equation number 1 here without the parameter of C2, because we already know that C2 here is equal to 0. So we use another boundary condition. Boundary condition at point number 2 here. So we substitute into equation number 1. Then we could get the value of C1 is showing like this. It's showing as this one. So and then we substitute the C1 here into equation number 1. So mean into this equation. So we substitute into the C1 here. So finally, we could write as this one. So and then we could simplify this term into this one. So this is the velocity distribution or velocity profile for this situation. Okay, please try this at home. Okay, so we go for tutorial number 5 here. So for example, we have a compressible flow occurs such that U is equal to 200 xy. So and then V 200 times x square plus y square, and the W is 0. Find the rate at which the density is changing at the point of 2 meter and 1 meter. So we here, so this is the coordinate. So you know that the question is showing the Cartesian coordinates. So they use x and y. So means that you need to solve this maybe by using the Navier-Stokes equation of Cartesian coordinate. So the density is given at this point is 2.3 kilogram per meter cube. So please remember that we are solving a compressible flow. So compressible flow means that there is possibility of the density changing at so many points. So we start from the continuity equation. So this is the full continuity equation that we could derive from the Cartesian coordinates. So and then we could simplify it like this one. So and here we cannot simplify the value of rho here because we are dealing with compressible flow. So that's why we have this term. And this term is actually can be simplified into this one. Okay, so we have the d rho dt, okay, with the capital D, and then we assume that the W here is equal to 0, so we could neglect the value of W here. So we could neglect the value of W here and also the W here. So, and then we could have this term. So we have d rho over dt minus equal to minus rho du dx plus dv dy. Okay, so why we rewrite our equation like this? Because the question is find the rate of the density. So that's why we need to create our equation reflecting the rate of density. So the rate of density is actually the terms that showing how much the density is changing over time. So we need to get the d rho dt here. So we have this term. Okay, so find what we should do from this term. So we know that we need to calculate du dx and we need to calculate dv dy. So from the data given in this equation, in this question, so we have u equal to 200 xy, so which is du dx is 200y, and v is this equation, so we could write dv dy is equal to 400y. So and then we have coordinate of 2 and 1. So and then if we substitute everything, so we substitute the value of density here, so we substitute the value of du dx and dv dy, we substitute the coordinates here into the value of x and y here. So and then we could calculate that dp d rho over dt is minus 1380 kilogram per meter cube second. So means that the density is become lesser and lesser because the negative showing you the reduction of density. Okay, so we go for tutorial number 6 here. So the x component of the velocity vector is measured at point A, B, and C, 5 millimeters apart as 11.3 meter per second, 12.6 meter per second, and 13.5 meter per second respectively. So means that this velocity is actually reflecting the velocity at point A, point B, and point C. And the condition here is incompressible. So means that the density is constant. It is a steady plane flow. So, and then we need to estimate the component y of velocity for the component y of velocity at 4 millimeter above point B. So means we try to estimate what is the velocity 4 millimeters above the point B here, but the y component of velocity, that you need to know that this is the x component and this is the y component. So we need to calculate what is the y component at this point. And then we need to calculate what is the acceleration at point B. So why the acceleration comes in this question? Because you know that our shape is divergent like this one. So the cross-sectional area is become smaller. So as you learn in fluid mechanics 1, so A1 V1 equal to A2 V2. So normally for incompressible flow, so if the cross-sectional area is smaller, so the velocity will increase. So means that when we have changes in velocity, so we must have an acceleration. So acceleration usually we have v2 minus v1 over time. So mean the changes of velocity will give us an acceleration value. So this is the answer. So we start with the continuity equation. So this is the continuity equation. So you could revise back to the notes previously. So and then we could summarize everything. So we know that it is incompressible. So means that the changes of density is actually equal to 0. So we lost everything, the terms here. So finally we could bring the rho to the right hand side, so we have 0. So and then we assume that there are no velocity for w, so finally we could say that du dx plus dv dy is equal to 0. So and then so this method is actually to find the value of y component of velocity. So because we want to get the y component of velocity, that's why we need to rearrange our calculation to have the dv dy here. So the dv dy here is equal minus du dx. So minus du dx here, okay, sometimes you need to understand the meaning of the meaning of the symbols that you are using in your calculation. So du dx here means the changes of velocity u along the x condition, along the x axis. So I take du dx here is actually the changes of a, b, and c here. So because we have a 3 point, so I think it is okay for us to take the value of a and c. So that's why I take 13.5 minus 11.3. So because this is the 13.5 is the velocity at C, and 11.3 is actually the velocity at A. So we just take a very rough calculation to know the velocity difference. So and then we take the dx here is actually the distance between A and C. So this is the dx. So because it is 5 millimeters apart, so means that the x is actually 10 millimeters. So you need to calculate by using the SI unit. So I think everybody know this one. So it will become 0.01 meter. So we calculate this one. So we get it is minus 220 meter per second. So we have dv dy is equal minus 220 meter per second. So we bring the dy here because we assume that the value of dv dy means the gradient between the velocity and the distance of y. So we bring the y to the right hand side. So we could substitute the value of dy here with 0.004 because the question is 4 millimeters above point B. So 4 millimeters means 0.004. So we substitute into this equation. So we get the dv here means the element of velocity on y-axis is minus 0.88 meter per second. So means that the velocity of y element is actually become slower and slower when it move on y-axis. So it means that the velocity here, okay, it's become slower and slower when it's moved on the y-axis because the velocity is actually negative 0.88 meter per second. So and then we need to calculate the acceleration. So the acceleration here, this is the equation. So I'm not showing you how to derive this one, but I think it is okay. You could find this into the in the textbook. So according to our syllabus, it is okay for you just to remember the equation for the acceleration. So the acceleration for x-axis here can be written as du dt plus u du dx plus v du dy plus w du dz. And then because it is a steady flow, so we assume that du dt is equal to 0. And then we take, because we are focused on x component only, so we say that the v and the w here is equal to 0. So we have all of these terms is equal to 0. So finally we only have this term. So we have u du dx, so we substitute the value. So u is 12.6 meter per second, and u dx is calculated previously as 220, and finally we could say that the acceleration is 2,772 meter per second, meter second square. Okay, next we will discuss about tutorial number 7. So we just use the same diagram. The velocity of air in a pipe is measured at points 5 centimeter apart to be 137, 147, and 159 meter per second, respectively. At the middle point, the temperature is 5 degrees Celsius. So mean at B here is 5 degrees Celsius, and the pressure is 124 kilopascal ABS. So ABS here means we are calculating this pressure by using the idea of absolute pressure. So I think you already know the difference between absolute pressure and gauge pressure. So if the term is written as in bracket ABS, so means that the pressure is in absolute unit. Okay, so the question is find the rho dx at the middle point of this steady and uniform flow. So you know that the flow is steady and uniform, and then we have air here. So air usually can be compressed, so that's why it's not mentioned here whether it is compressible or incompressible. So usually if you are dealing with air, so please be careful, because sometimes you need to take air here as compressible fluid. So means that if you use Navier-Stokes equation, please do not easily ignore the value of the density of the density. Okay. And another thing, because the question here gives you the value of temperature. So because air is a gas. So gas is normally very sensitive with temperature. So mean the increment of temperature will expand the gas. So means that we need to calculate that with the idea of with compressible flow. So this is the continuity equation. So we have this term. I hope you could remember this term. So because it is steady, so we take d dt is equal to 0. So and then it is a uniform flow. So means that the velocity is remain constant at a distance. So we take dy dz dy and d dz is equal to 0, and means that we could only have this one. Okay, so please, as I said previously, the value of rho here is need to be maintained because we are dealing with air. It is not state in the question that this is incompressible or compressible flow, but you must know that when the temperatures come in, when you are using gas, so normally it will change the density of gas because gas is very sensitive with temperature. You learn this in thermodynamics, in applied thermodynamics. Okay. So at the middle point, because we are focusing at the middle point, so we know that from the question, so we have question here, so we have 137, 147, and 159. So the middle point, the velocity is 147. So because we are dealing with air, with gas, we need to calculate like this one. We need to determine what is the density of that air for the present condition, for the first condition. So we could calculate the value of density rho is equal to P over RT. So which is P is the pressure and R is the ideal gas constant and T is temperature. So P here is 124 because the question here is given in kilopascal. So we need to change, we need to add 1000 there to reflect the value of kilos. So we have 124 times 1000. So and then R is 287. So I hope you still remember what you learned in thermodynamic 1. Okay, so because it is common. And the value of R, the ideal gas for the ideal gas constant, the gas constant R is gas constant from is different from gas to another gas. So means that for air we are using 287. So and then the temperature is 5 degree. You need to convert into the K into Kelvin. So we have this term. So if you calculate, we could find that the density is actually at the first point, at the initial point is 1.554 kilogram per meter cube. So and then we need to fulfill this equation actually. So we need to calculate what is the value of du dx. So we could calculate du dx by using this idea. So I explain this one. So you calculate the difference of velocity. So and then we divide into the difference of distance for x-axis. So we get 220 meter per second meter, like this one. So and then we could calculate u d rho dx is equal negative rho du dx. So we substitute the value of negative rho here by using this value, and we substitute du dx by using 220 as we calculated here. So and then we could calculate that d rho dx. Okay, and then we bring the value of u to the right hand side. So the d rho dx mean the changes of density along the x-axis is 2.3257 kilogram per meter by the power of 4. Okay, so